the history of telecommunications a little bit, the basic notions used in telecommunications. I will be presenting the OC and TCP/IP models, MAC and VLAN particularities, spanning tree protocol, ARP and the other two forms of ARP, and ICMP. Tomorrow we will go through the rest of the agenda. Firstly, history of telecommunications. The first telecom system was smoke and drum signals used since ancient times. The first network was built in the 60s, and it was called ARPANET, and it was initially it had 4 nodes connected throughout the USA. The first letters transmitted were LO from login from Los Angeles to Stanford. They said that it was built to resist to a nuclear attack, but it was so frail that the network crashed after the first 2 letters sent. ARPANET had 213 nodes by 1981, and it was formally closed in 1990. The Internet appeared in 1983 when ARPANET was split in 2 networks. It was MILNET, the network military ARPANET, and the rest was still called ARPANET, and together they were called Internet, which comes from Intergalactic Computer Network, and the notion was used to refer to the both networks. An RFC is a request for comment, and it refers to a document published by IETF, which is an organization that supervises all the Internet standards, and it describes methods and behaviors applicable to the Internet. The first RFC was for describing host software. It was written in 1969 and describes how the ARPANET equipment is supposed to function. It refers to both hosts and interface message processors, which are the first version of modern switches. Ethernet refers to a family of network technologies for local area network that provides services up to and including the data link layer described in OSI model. We will see the OSI model further on. The MAC addressing is one of the most known features of Ethernet. We will go now through some of the basic notions. The answers to all these questions are at the end of the presentation. You can look them up later if you want. So, a datagram refers to the format of the packet as defined by IP, which is the Internet Protocol. Encapsulations refers to adding delivering informations, which are called headers, that are received from a layer above. We will detail the encapsulation later in this presentation. When a datagram is too big to be processed by a device, it will be fragmented, which means it will be split into smaller packets and sent sequentially so the device can process them. We have the notion of MTU, maximum transmission unit, which is between 150 and 1,500 and 9,000 without the IP header. Multiplexing, it refers to the delivery of data to the correct software in a host. It uses port and protocol numbers. The port number may refer to two things. One is a physical input-output entry in a device, and it can look like a 5/1. We will see later in a practical example this physical port. Or it can refer to a unique number inside the transport layer, and it identifies an application. For example, the ACP uses 67 and 68 as ports. On a Unix device, you can see the ports in a file called services. I will show you now this file just so you can have an idea about it. In this white screen here, I have a host, and the two green screens above are two devices that can be configured to be also switches and routers. I will show you now the port file, which is in ETC services. Here you can see you have, let me show it in full. You have, for example, for MSP, the port 18, or SMTP, which is a more common one, 25, for Telnet 23. You can look it up for all of them here. Going back to the presentation. So we covered port and for the both uses of them. Protocol, it refers to a number used by IP to identify a transport protocol, such as ICMP, TCP, or UDP. These numbers can be seen on a Linux device. I'll show them to you as well. In the file ETC protocols. Here we find UDP has the protocol number 17, or IPv6 has 41. There are a lot of them. PIM, which is a protocol for multicast, is 103, and so on. A socket is a pair formed by an IP and the port number, which identifies uniquely in a network the process. This kind of pair of socket, one for transmission and one for receiving host, define a connection for connection-oriented protocols like TCP. You have the well-known ports, like I shown you, like for Telnet we have 23, and you can define your own port numbers for applications you define, and they are in a range that doesn't coincide with the well-known protocols. It is very important to know the difference between a host, a hub, a switch, and a router. A host refers to a computer connected to a network that sends packets or receive packets. A host will not forward any packet. A hub is a device that sends every packet that it receives throughout all the other ports. It doesn't do any calculations, any decisions to where to send the packet. It just floods it throughout the network. A hub is a layer 1 device per OSI model. A switch will do a bridging between a subnet. From one host, if you send a packet to a destination with a certain MAC, the switch will deliver that packet to the explicit mentioned host, will not flood the packet to every host. That is the difference between a hub and a router. At a switch level, we only need to have a MAC address. A router will forward the packets between two different subnets. We need to have IP in order to do the forwarding, and this is a layer 3 device. A default gateway is a router configured on a host that will receive all the packets that a host doesn't know where to send. You have to have a default gateway on every host. The difference between LAN and VLAN is that VLAN does not have to have restrictions on a physical from a physical point of view. You can, for a LAN, all the computers linked to a LAN have to be connected to the same device, while for a VLAN you can have hosts connected to different devices, physical devices, but they can all be into the same subnet only by adding them to a certain VLAN. Also, on a switch, you can divide the ports. If you have a switch with more ports, you can divide them into separate VLAN, simulating this way 3 different physical devices. The OSI model is an architectural model that refers to systems of communication. This is not used in practice a lot, but is very good for teaching purposes. And usually when we refer to layers, L1, L2, L3, we refer to the OSI model, even if we are talking about IP protocols. We are going to start from down here, from down to up. We have the physical layer first, which defines the electric and physical specifications of the device, especially the relation between the device and the transmission environment, like a fiber optic or a copper cable. To data link layer, we have the means to transfer the information between two nodes in a subnet and to correct the errors that may appear at physical level. Through the layer above, network layer, this provides the means to transmit information from a host from a network to a different host from another network, and it maintains the quality asked for a transport layer above. The transport layer assures the transfer between end user. This transfer is made transparently and assures the fiability of the link by making flow control. Here we do the segmentation and desegmentation of larger packets, and also error control. At session layer, we control the connections between local and remote applications. We make sure the sessions are gracefully closed, and also make sure that the verification of the session is made here. The presentation layer establishes a connection between the entities of the application layer. It does the translations of format between the application layer and the session layer, and it is also called syntax layer. The application layer is the most close to the users, and interacts directly with the software applications. It identifies the communication partners and the resources, and it also synchronizes the communication. The TCP/IP model has only 4 layers, and they are not as rigidly defined as in OSI. Each layer has a piece of information which is called header, which ensures the properly delivery of the data. We will start again from the lowest layer, which is the network access layer, also called link layer, and assures the transfer the transfer of packet between the interfaces of 2 hosts that are on the same link. The notion of 2 hosts being on the same link means they are connected to the same VLAN. The internet layer makes the datagram exchange between subnets. So you have to have IP address, and the main protocol of this layer is IP. The transport layer, it's exchange message between 2 hosts, either from the same subnet or different subnets, and offers a uniform interface which hides the connection topology of the network. At this level, we also do flow control and error correction. The application layer, which is a process-to-process layer, the application can communicate with other processes or applications from another host. The partners in communication at these layers are called peers. Protocols that operate at this layer are FTP or SSH. Here we have the diagram of encapsulation. Let me just, no. Okay, so just for this slide, I will show it in the small window. Here at the application layer, we populate the packet with the information we need. Like for a telnet session, we say the user and password, and we put it in a packet. The layer above, the transport layer, we take the data above, and the layer does not look into the packet to see what it is populated with. It just adds its header with the protocol number and the other information that are described in the RFC. The layer below, the internet layer, will take the data above, and the TCP header for the IP layer is just another data. It doesn't look into it, and it adds its information. The same for the network access layer, which will add the MAC. The sender starts constructing the packet from up to down, from the application layer to the network access layer, and when it will reach the receiver side, it will be decapsulated. It will be peeled off the headers for every layer above, and at the end, the application will interpret the data. We'll check, for the example I given you, the address, the user and password, and we'll see if they are correct and if the telnet session can be started. In the picture below here, you actually have a captured packet describing all the headers. You have the Ethernet 2 format, which is a layer 2 header, which defines here the MAC source and the MAC destination. You have the IP header, which says the IP source and IP destination. You have the UTP, the transmission protocol. You have two ports here. These both ports are user-defined numbers. They aren't well-known numbers for the transmission protocol, and then you have HyperNet Transfer Protocol, which is an application. It's at the application layer, the actual information that is transmitted. Okay. We were going to define now the Internet Protocol, which is not based on a connection. If a protocol is based or not on a connection, it means that it has a mechanism to make sure that the destination actually received the packet. This means that we have a connection protocol, connection-based protocol. So IP is not such a protocol. It relies on other protocols to make sure that the destination actually received the data. The only check that it makes is the checksum, which is a number calculated for the IP header only, not the data. In the packet here, you see it here, header checksum. It's correct. It is written in hexa in the packet. The IP protocol routes datagrams to the remote hosts. And also here we do the fragmentation, the one that I described above, when you have a packet too large to be sent whole. On the sending host, you do the fragmentation, and on the receiving host, you do the reassembly of the packet. The IP header contains the source and destination IPs, which are here in these lines. It also has a time to leave, which can refer to the maximum nodes through which a packet can go. If it goes through more than 64 packets in this case, then the packet will be dropped. And it also has some other bits and information that can be used by the receiving host. TCP and UDP are transmission layer protocols, and they are the most commonly used. TCP is a connection-oriented protocol, and it has a mechanism to assure the data delivery, which is called positive acknowledgement and retransmission, shortly called PAR. It is based on a three-way handshake, which consists in delivering three segments. One is the synchronize sequence number. The other one is acknowledgement, which is sent by the receiving host. And after these two messages are sent and received, the data is actually starting to be transmitting. When the transmission ends, the TCP packet will have a FIN bit, which will announce the receiver that there are no more packets to come. Also, the TCP has two fields called sequence number and acknowledge numbers, which are set in the TCP header, that assures that all the packets are received. When a sender manipulates a packet, it will set a sequence number, and the receiver has to reply with the same number put in the acknowledgement field. If there is a packet that it didn't has the acknowledge number set, the sender will retransmit the packet. So this is how the transmission is assured. For UDP, we don't have any mechanism to make sure that the receiver actually got the packet. Because all this information about the sequence and acknowledgement numbers have to be put in the TCP headers, it has to have a lot of information, and it may create an overhead over the network. The UTP has only a few fields, so it's a low overhead. TCP is recommended for a big amount of data that needs to be transmitted, or for a connection that must be made sure that the receiver got it. UDP is recommended for a smaller amount of data, and it is fit for protocols that have in itself a way to see if the receiver got the information. Such applications are RIP, DNC, or DACP. For example, you will see tomorrow that DACP has a model which it in itself relies, it checks if the server or the client actually received the message, so it does not need the transport protocol to do that. It is done at the application layer. TCP is recommended for safe delivery of data for applications like FTP, Telnet, or SMTP. We will start now talking about MAC and VLAN. The MAC address, maybe you heard about it before, it identifies the physical device. Here you have an example of a MAC. It consists in 6 numbers which are written in hexa. The first 3 numbers refer to the organization that sells the device, and the rest 3 identify the device itself. Computer has its MAC predefined. It comes with a MAC from the factory. You do not configure it. There are devices that permit setting a MAC, but you cannot be sure if you set it that it is still unique. While the MAC that is given by the factory, it is surely unique. Here, in the first byte, the last bit from the first byte from the MAC address, it is called the multicast bit, which means if this bit is set to 1, the packet will be delivered to all the nodes in the subnet, regardless of the rest of the information. While if it's set to 0, it means it's a unicast packet, and additional checks will be made to see to whom we have to transmit this packet. For this, because of this differentiation of the bit, the multicast bit, we define layer 2 multicast address and unicast address. The layer 2 multicast address will also always have this bit set. Here you have an example of a multicast MAC, which here has the bit set, while a unicast MAC will not have it. The broadcast address, the broadcast MAC address, which is all bits set to 1, translated in hexa means FF for all the bits. It's a reserved layer 2 multicast address because it has that bit set. When you send the packet to this address, will be forwarded to all the nodes. A correspondent IP to this MAC broadcast MAC, it's the same, all IP bits set to 1, which translates in 255.255.255.255. The Ethernet header may have different formats depending on the standard that it used. It may be 802.3 or 802.2 LLC, or the most common one is Ethernet 2, which is described, it's shown here, and it's the most simple one. You have the source MAC, which is given here. You can see the unicast bit is set. It's the value of the bit is 0, and you also have the globally unique address. The destination MAC, the same, is a unicast address, and you have here the type of the packet, which is 08. It's the number for IP protocol. A VLAN can include one or more ports. You associate a VLAN with an IP, and if you don't have an IP on a VLAN, then it will act as a switch. If you put IP on the VLAN, then it will act as a router. The IP you assign to the VLAN, it's reachable through all the ports in the VLAN, and it will identify the VLAN itself, not some specific port. The mapping between port and MAC is contained in the MAC address table. Here in this show, you have the MAC entries from a router, and you can see here the VLAN ID in this column. The status shows if it is locally configured or it is a MAC learned from another host, the MAC address itself, and the port where the MAC is learned from. In the red line, the red highlight, you have a remote host with this MAC, which is learned on port 5/12, and with the green highlight you have a locally VLAN with a locally MAC, and the port is CPP, which means locally configured. They are both on the same VLAN. The green one is local, the red one is remote. I will show you an practical example how you can create a VLAN, and you can add more ports to it. And we will see the MAC table. Here we have the device I told you. We can it can be made both a switch or a router. We will make it a switch right now. So the command itself is not too important. It may differ from from one device to another. I will show it to you just so you have an idea on how we can actually put into practice these notions of VLAN and physical ports, and adding more ports to a VLAN and the MAC table. So we will create a VLAN now. We can give a number to the VLAN. I will put 200. The type, refers to the spanning tree used for this VLAN. I will give you more details about the spanning tree later on the presentation. Right now, we'll just need it to configure the VLAN. Right now, we have this VLAN. I show it to you. Show interface VLAN. And we see here we have two VLANs. One is a default VLAN. It will always be configured by default. You cannot delete it. And it contains by default all the ports available in the device. And below we see the VLAN I just created, which currently, you can see here port members. Currently it doesn't have any port because we didn't assign any to it. Further on, we will add 2 ports in this newly created VLAN. We will add in VLAN 200 ports 617. This is an example of the physical port I talked to you about. 6 refers to the slide and 17 refers to the actual port. On this device, we can have 10 cards of input-output, each with 48 different slots. So we have the card 6 and the 17th entry in that card. And we are adding 2 ports to it, 617 and 644. Which it doesn't like it. Let me give a... Okay, I've just shown you the ports so I can see that the input-output card is available. And let's try again. I added a space here, that's why it didn't let me configure it, so you have to give no space between the ports, just the comma. Okay, now we have a VLAN with 2 ports in it. Show interface VLAN will give us the 2 ports here. Now we see that we have them removed from the default VLAN, the 1, and put into VLAN 200. Okay, so now these 2 simple commands are used to create a VLAN and add some ports to it. At this point, we have a switch that is configured. It has two ports. On each end of the port can be a switch, a router, or a host. In the topology I have, the 2 ports are linked to the other router that I have here. Going on. Okay. If you have questions, please write them down and write also the slide when you see it, and I will be answering to it at the end of the presentation. Okay, so further on, there are a few rules that are used in the switching in switching the packets. This is called layer 2 switching, and the rules are as following. Okay. When a frame is received by a switch and it does not know the destination MAC of the address, the frame, it will be sent to all the ports except the ingress port. We use the notions ingress and egress ports to define the port on which a packet came and the port where a packet is sent. The ingress is the incoming port and the egress is the exterior, the sending to port. So if we have a packet that we don't know to what port has to be sent, we will send it on all ports. When the destination host replies to that packet, its MAC will be added to the MAC table with the port on which it came. So we now have an entry for the MAC destination to the relevant port. When a second packet is sent to the same destination, we have the mapping in the MAC table, so we will send the packet to the specified port, to the correspondent port. The entries in the MAC table usually have an aging time, after which they are removed from the table. Every time you send a new packet to that destination, the timer is refreshed, so the switch knows that that MAC is still used. If you don't use it for the expiry time, then it will be deleted, so we don't end up having a too large MAC table with entries that we don't actually need. Okay, we've seen that we added 2 ports in a VLAN, but we can also have the reverse, where a port is added to more than one VLANs. This practice is called VLAN tagging. It is defined by the standard 802.1q, and it usually is shortcutted to .1q standard. And you can see it here in the packet I've put here. You can see 800.1q header. And it allows for a packet that comes through a port to identify the VLAN on which that packet has to be sent. This header contains here the ID of the VLAN which we have to use. If an untagged packet is received, then it depends on the implementation of the device if the packet is dropped or further checks are made, like you can check the IP in the packet to see if you can identify the VLAN. But it is not imposed, this behavior is not imposed by the RFC. I will show you now how we can add a port to multiple VLANs. Here on the same router, I will delete the VLAN, I will remove the ports from the VLAN I just made. So it's VLAN members remove from VLAN 200, ports 617 and 644. I will now enter in one of these ports, interface, gigabit Ethernet, which is the type of the port, let's say 617. And I will enable the encapsulation, which is made through encapsulations.1q. Here is the protocol I just told you about. So now we can add this port to more than one VLAN. If I didn't enable this .1q encapsulation, when I would try to assign the port to a new VLAN, it will just be removed from the current VLAN and added to the new one. By enabling the .1q, I can have it in several VLANs. I will now create a second VLAN, 300. Put it in the same STP. And I will add the port to both 200 and 300 VLANs. First to 200, 17, and then to 300, to VLAN 300. And now show interface VLAN members. No. Okay. Okay, and you can see here through these two lines that both VLAN 200 and VLAN 300 have the same port. When packets will be sent or received through this port, 6/17, the header, the VLAN tagging header, which it's shown here, will be added to the packet, and then the rest of the data will be put on. Okay. We now start talking about the SDP, Spanning Tree Protocol. This protocol is used mainly to prevent the broadcast storms. What is a broadcast storm? When you have a loop in the network, as shown in this figure here, you have three routers. They all have ports in the same VLAN, and thus you create a loop. When you have this kind of configuration, and you send a broadcast packet, let's say from router 2, the packet will be sent for both links. When this packet reaches router 3, it is a broadcast packet, so it will send back through router 2 and router 1 the same packet. Same for router 1. It will resend the received packet to router 2 and router 3, because this is what broadcast means. You receive a packet that you multiply to all the nodes in the network. So for each time that one packet reaches one of the routers, it will be multiplied and resent to all the network, and then again and again and again, and at some point you will be using the whole resources to process a packet just because you have a loop in the network and you do not need to receive that packet just once. You don't have to resend it. So this is what a broadcast storm means. Going back. Okay, an SDP, a spanning tree protocol, with make a map of the topology, and it will block some ports in order to eliminate this logical loop. From here in this screen, you can see that if we have three routers with which make a loop, one link will be shut down. Or if we have two links in the same from two different routers, and we have more links between those routers in the same VLAN, then we will also be blocking two of the links. Only one remains active. I will show you this situation on the two routers I have. The STP is a layer 2 protocol, which means we do not have to have IP in order for it to function. Okay. So here we have two routers connected between them. I will configure again the VLANs in order to make that two VLANs with two ports, one VLAN with two ports in it. So this will remove the VLANs I previously configured. I will go into the port 617 and remove the VLAN tagging. So it doesn't interfere with the new configuration I am making. So I am creating VLAN 100 with the spanning tree 0, and the same I will do on the other router. VLAN create 100 and the port, the type of STP 0, the number of the STP 0. Now I will add the ports. In VLAN 100, on this device, the ports are 4/17 and 4/44. The same on the first device. Now, in order to have the ports functioning, we have to enable them. So I will go under their configuration interface, Gigabit Ethernet 6/17 and 6/44, and I will give a no shutdown command which will bring them up. The same for here. Interface Gigabit Ethernet 4/17 and 4/44, and the no shutdown command. So right now we can see some messages here that the links are up, and if I issue a command of show interface Gigabit Ethernet 4/17 and 4/44, we can see here we have the status admin, which means that we given the no shutdown command, and the actual state, the operational state of the port, which are both up, which means the two ports are usable. Since we've put them both in the same subnet, in the same VLAN, we should see that the STP blocked one of these ports. So I will issue the command show spanning tree. I will explain later what MSTP means. 6/17 and 6/44. Right now they are both in forwarding state because STP usually takes a lot of time to make the topology, and it will take a bit of time to update and block one of the ports. Let's see on the other device. Okay, so here we see that the 4/17 is in forwarding mode, and it is the link that is used for transmission between the two routers. And the 4/44, it's an alternate port, and it's in a discarding mode, which means we will not use that link for communicate with the other router. Here we still have them both usable, but only logical, because this discarding mode here will not permit for the packets to be processed. Okay. So I just illustrated this scenario here when we have two routers with multiple links in the same VLAN. I told you that STP usually takes a lot of time to make the topology, especially if it's something with a lot of components. So they created a rapid spanning tree, which uses the same topology, but the same practice, but it is done more rapidly, this convergence. And also multiple spanning tree protocol, which permits to do a spanning tree just for a VLAN. On the opposition, a simple spanning tree protocol will make a topology configuration for the whole network, regardless of the VLAN information, not of the VLAN information, regardless, all the VLANs will be in the same tree, while on the multiple spanning tree you will have a different tree for each VLAN. That is the difference. So the simple spanning tree, it also makes a calculation for the most efficient path from one source to another. It will by creating this map of the network. It will put the ports in a collection of it will put all the ports in a spanning tree. You can imagine the structure, the tree structure, and they all be put in a group called spanning tree group, STG. Each group is independent through another. So when I showed you the the untagged port, the one that we don't enable encapsulation.1q, can belong only to one spanning tree group, while the tagged ports can belong to more than one spanning tree. The nodes communicate, the STP nodes communicate with each other using a bridge protocol data unit, which is a message that contains information about MAC and IP priority, used to create the tree with the ports. Further on, I will tell you about the ARP, which is used to make a mapping between an IP and a MAC address. The ARP table can be seen on a host with the command ARP-N, or just ARP, but this -N will be making it a little bit prettier. You have here the output of such a command. And what I've done in this example, it's I've shown the ARP at the beginning, the ARP table, and I see here that I have two IPs with the correspondent MACs learned on interface Ethernet 0. I tried to access 3 different hosts, which is 60, 62, and 63 different IPs. And then I look again at the ARP table. Here I see that all the 3 hosts were added to the ARP table, but 60 and 63 didn't answer me back, so I have the incomplete entry. I only have the IP, but I do not have the MAC because it didn't reply. The host didn't reply. And for 62, I have learned the MAC because it was given to me by its reply. So on Linux, you can add a MAC in a new entry in this ARP table only when you initiate it. On Windows, the MAC table, the ARP table is populated in a different mode, which is a bit more risky, because if I receive a MAC address with an IP from a malicious source, then that entry will be in my MAC table and I will be sending packets to it. On a router, we have the distinction between local and remote interfaces. Here we have the same as with the MAC table. We have a local IP with a local MAC address. Here it is. And we have a remote IP with its MAC, and it's learned by port. And it is said that it's dynamic. We also have the time to leave, the time for which that entry is learned, so we do not end up with a huge ARP table that it's most of its entries are not used. When this time expires, the entry is deleted. If we receive a packet from this source, then we update the timer and extend the longevity of the entry. Further on, I will explain in detail how we populate the ARP table. For example, we have an application, let's say Ping, which is an application used to verify if the remote hosts are available. At the beginning, we have this information in the ARP table, which means that we have the self here. We have IP 10.1.1.1 with its MAC learned, and another entry which is learned dynamically, and it's for IP 10.1.1.2 with its remote MAC. We see here that this IP refers to host B, and host B does not have the reverse MAC. It does not have the MAC of host A. This can happen because the entry expired. It may be populated at some time, but the entry expired, so it is possible that we have the MAC learned in one host, but at the remote host it isn't learned. So we have this application which wants to access 10.1.1.2. At this point, the application searches in the ARP table. The ARP table receives the request for this IP. It finds the entry here, and it is returned to the application. The application constructs the packet, and it will be sent to the correspondent MAC, and the correspondent port will be taken by this MAC from the MAC table. Then the packet is sent to host B. Host B will learn the MAC of host A and will respond to the ping request. Then host A wants to send a ping to a different IP, 10.1.1.3, which is correspondent to host C. Host C has only its own entry in the ARP table. So the application sends a request to the ARP table for this IP. The entry is not found in the ARP table, and it will send a broadcast ARP request, which means a specific packet of ARP request will be sent to all the node. It's ignore the request. Host C will receive the broadcast packet. It will see that is for its IP. It will save the entry of host A, the MAC of host A, and it will reply with its own MAC. When host A receives the reply, it will save the entry in the ARP table, and it will return the MAC, the requested MAC, to the application. The ping application will populate the packet with the given MAC, and it will continue sending the packet per usual mode. This is how we create entries dynamically in the ARP table using ARP packet. An example of such packet we have here in the upper part of this picture. We have a request, address resolution protocol request, and it will have you can see here this is a capture made by Wireshark, which sometimes interprets the data in the packet, and it has the request says who has packet, who has the IP, this IP here, and reply to the IP here. And in this request, we can see the sender MAC address, which is the MAC of IP 11.126.20.172. And we request the MAC of this IP, 173, the same subnet. And at the target MAC, we put 0 because we don't know its MAC. In the reply, which is below here, we have the reply. The sender MAC is 173, this host, and it puts its own MAC in the sender MAC address. And the target is the original requester, the version, the MAC from here and IP from here. So this is a ARP reply. Based on this kind of packets, you create the ARP table. You can see here it's over, you have the Ethernet to header and then directly the RP information. A gracious ARP is either a request or a reply that do not have a correspondent. The request does not expect a reply, and the reply is not given to any request. This is usually sent by a router when it comes up in order to notify the host that in order for the host to have its MAC. So this is useful for a default gateway that I told you what is in the first in the second slide. If a host wants to send a packet to the default gateway, it has to know its MAC. So for the router to make sure that its MAC is learned, it will send a gracious ARP. It doesn't matter if it's a request or a reply. And it is also used to detect IP conflicts when you have the same IP but with different MACs. This is made with this packet is constructed with a flag here. it is gracious is set to true. In the previous example, I will show you the slide again. Here, the gracious flag were set to false. It's a normal request reply. In a gracious request, or in this case, we have a reply, a gracious reply. We have the the is gracious flag set to true, and we also have the same information to both sender and target. It is not destined for somebody specifically. It is destined to everyone, so that they know the MAC of this IP. Reverse ARP, it is used by hosts who usually do not have a permanent storage device to dynamically find the ARPs when they only have their MACs. We said that the MAC is given by the producer, so we always have a MAC, but we need to have configured an IP in order to make forwarding, to send packets to a different subnet. In order to use reverse RP, we need a server on a network that will have the mapping between IP and MAC. This server will reply to RARP requests if the mapping is found in its database. The same format of RP is used, but different codes. For request reverse is 3 and for reply reverse is 4. In a normal RP request and reply, numbers 1 and 2 are used. The request for a RARP packet is sent broadcast because the host requesting it does not have an IP assigned, and it doesn't know the IP of the server, so it will reach throughout the whole network. While the reply to the RARP request, it will be sent unicast. It will be sent specifically to the host requesting the IP, because the server, the RARP server, knows the MAC of the requesting host. This protocol is obsoleted by DHCP, and it is presented only in learning purposes. InARP is used to determine the IP of another node from its MAC. In this in the normal RP, we know the MAC, but we do not know the IP. Both the request and the reply are sent unicast because we know the MAC of the destination. And if a host receives this kind of message, an InARP message, it will reply to it automatically, because since it is sent unicast, it is supposed to be destined to it. As well as for RARP, the same packet format is used as in ARP, with different different codes, 8 for request and 9 for reply. This kind of packet is usually used in ATM networks, where we know the MAC of the device we are searching, but we don't know the IP. So to sum it up, for RP, we know the IP, but we do not know the MAC. For RP, we know our own MAC, but we don't know our own IP, and we're trying to get it. And in ARP, we know the remote MAC, but we don't know the remote IP. So the difference between InARP and reverse ARP is that we are detecting the IP from the MAC, but for reverse ARP we do it for ourselves, and in ARP we do it for a remote host. ICMP. It is a part of IP protocol, and it is used for control and reporting information throughout the network. When an error is detected, an ICMP packet is it's created by the destination, and it is sent to the originator of the packet for which we detected the error to announce it that there is a problem with the packet it sent. These ICMP packets are treated as special packets, and they are different from the normal IP processing. It operates based on a type and a code that are predefined in order to detect what the problem is. ICMP has several errors that defines, and I will present it briefly, the most important ones. The flow control refers to the case when we are sending packets too fast for the receiving host to process them. If this case is encountered, the receiving end will reply with ICMP source quench message back to the sender, which will tell the sender to slow down with the rate of sending. If we have a performant device working with an older device, we may encounter this kind of situation when the receiver is the older device. It cannot process the packets as fast as the modern device sends them. Another case when we use ICMP is to detect the unreachable destinations. When a host sends a message to a default gateway, it does not know the destination and it sends to the default gateway. I will detail this process when we will reach the routing table, I think tomorrow. The gateway will search the destination in its routing table, and if it is not found, then an unreachable destination is sent to the originator so that it doesn't keep sending packets to that destination. Below here I have an example, a capture of this kind of packet. As I said, we have here the type. The type of the error is destination unreachable, which is 3, and the code of the error is as well 3, which means port unreachable. So most likely this when this packet was sent means that the port wasn't up. We are trying to send a packet to a destination that it has a failed port. Another use of ICMP is checking remote hosts. This is the application ping I talked to you about before, and I think everyone heard of it. Is using the ICMP packets echo request and echo reply to determine if a remote host is operational. It only requests if this IP here given in the internet protocol message is up, and the reply, the echo reply, it's responding by giving this reply. It acknowledges that the requested host is actually available, is up. Another use of ICMP is redirecting routes. You can have a situation when you have 2 gateways in a subnet, and one is for a host. One of the gateways is a default gateway, while the other one, let's say it's a link to the exterior, to the internet. A host will send the packet to the default gateway, but this gateway will acknowledge that the packet should be sent to the other gateway linked to the internet. So it will reply with a redirecting route, a redirecting message that we have here, and it will say to the host, please use the other gateway because it's more suitable than me. This message can be used only when all the three participants are in the same subnet, the two gateways and the host. Another type of packet, the control packets that ICMP sends, are to check the time to leave, to check the number of hops between the source and the destination. Also the timestamp, which refers to the clock that is configured on both devices, and we want to check if they are synchronized, and a lot of other informations that are defined in the RFC of this protocol. Here I have a printout of the control message packet that says that the time to leave is exceeded, which means we forwarded the packet, and at a certain hop we discovered that we reached the maximum number of hops, and we sent back this control message in order for the source to either increase the allowed number of hops or to stop transmission. The source can decide either way depending on how its implementation is made. Further on, we will talk about the IP address. Until now, we talked about how we use the MAC, how we forward, how we send packets inside the subnet, and now we configure an IP for a VLAN, and we have a layer 3 either host or router. We have to make the separation between these devices. An IP address has two parts, a network part and a host part. The ranges of IP, firstly, an IP has 32 bits separated in 4 bytes, and the first bytes will define the network part, and the last bits will define the host part. The maximum range of IPs are separated in 5 classes. The first 3, A, B, and C, are used for addressing. The class D is used for multicast, and the class E is used for experimental purposes. The difference between the first 3 classes is made by the first bits in the network part. For class A, we have the first bit 0, and the rest can be any value. For class B, the first 2 bits must be 1, 0, and the rest can be anything. And for class C, the first bits have to be 1, 1, 0. Thus, when you translate from binary to decimal value, you will see that you can use from a number through another number to define the classes. Okay. The standard structure of an IP can be locally modified by using the host bits to define a network. like when we have here, for example, from class A, for host, we have 24 bits to define a host. And we can use some of these 24 bits to add to the network part. This way, we create more networks and reduce the number of hosts per network. The newly created networks are called subnets, and the number of bits used to define the network part is called a subnet mask. For example, here we have an IP 10.1.1.1/24. This 24 means that 24 bits are used for network part and 8 are used to define the host number. We also have some special IP addresses. An address with all host bits set to 0, it will refer to the whole subnet. We have here an example. You have 10.0.0.0. This is an IP from class A. If you define the mask of 24 bits, you will have the subnet 0.1.1.1/0. So the first 3 bytes will be for network, for identifying the network, and the last 8 bits, the last byte, will be used to identify the host. The reverse, when all the host bits are set to 1, we are having a broadcast address. Here, all bits set to 1, translated in a base in 10 decimal base, it means 255. So a broadcast address, an IP broadcast address, is used to refer to all the nodes in the network. And a packet sent to this IP will be replicated to everybody from that subnet. A normal unicast address is this one here, 10.1.1.10, from the same subnet. It refers to the 10th host from subnet 10.1.1.1. And these are the differences between the IPs inside the subnet. All host bits 0 means to the whole subnet, but you do not use it to address it. It just defines the subnet. The broadcast address, it's used to send to all the nodes in the subnet, and the unicast address is used to identify a specific host inside the subnet. I will start now talking about the ACP. I don't think we will finish it today, but I will tell you the most what we have time to present from it. The ACP is used to obtain an IP dynamically. Usually you have the possibility to assign a static IP. I can show you how to assign a static IP on a host as well as on a router. Here. We have, this is a host. The white screen refers to a usual PC that you may have. And I can configure an IP with, let me see, I will show you first the IP that is configured. The command is ifconfig. It's just for Linux. You do not need to remember it, just so you have an idea about it. And I want to see on Ethernet 0 what IP I have. And here I see that I have IP, the given IP, the broadcast address, which is with the last bit set, the last byte is all set to 1, and the mask that I have, which means that only 30 bits are used for mask, as a mask. They are used for network. So this is, if I want to configure an IP, I just add it here. To the same command, and I put slash the network. If I want to change the mask, I can put another mask. This is how I configure the IP, a static way. I will not change it, so there won't be any issues with the connectivity. On a router, we have the previously configured VLAN, show interface VLAN. We have VLAN 100. I will enter the config mode. I will enter the VLAN configuration interface VLAN 100. And here I can add an IP to it. IP address, let's say 100.1.1.1 on 24 bits. This is the mask of the subnet. It means we're using 24 bits for mask and only 8 bits for host. I will show IP interface. And here I see that on VLAN 100 I have the configured IP. If I configure an IP on the remote router, it has to be different from the one we just configured, because then we will have two devices with the same IP, which is a conflict. One of them will be blocked. IP address 100.1.1.2/24. The mask has to be the same because we are defining the same subnet. Show IP interface. Okay. Here I issued a ping, which uses the ICMP message, type of message, as an application, as the ping application uses the ICMP packet to determine if the remote host is up. So here I received the message that the host is alive. It's a message to say that we can reach via IP the remote router. This is how we transformed the VLAN from a layer 2 device when we didn't have the IP, we only have the MAC address and the ports inside it. Through a route, we transformed it to a router by adding an IP to it. So this is how we created the static IP. We configured the static IP. This kind of configuration works well only when we have small networks. If we have big topology, if we have a lot of devices inside our network, then it will be very tedious for an administrator to configure statically all the IPs inside that network. It is also subject to human error if we configure twice the same IP, or everything we do not give a correct subnet mask, and then the packets will not be correctly forwarded. So as an alternative to the static configuration, we have the protocol called DHCP, and it is used to assign IPs dynamically. It also allows the host to be configured with other parameters than IP. It is based on a client-server model. You can see in the diagram here we have 4 different subnets. They are linked through a device where we can configure a DHCP relay or not. You can have one server that offers IP to multiple subnets, to both these 2 subnets that don't have any server, or we can have a subnet where we have more than one server. They can be in a backup mode. If one fails, the other one can take over. And they both can be active in a subnet, and in this kind of situation, usually just one offers an IP to the host, and the other one just makes sure that the primary server is up and running. DHCP can allocate IPs to 3 different mechanisms. One is automatic allocation, which means we assign an IP permanently to a host. It is this is done by extending the time for the time that a host can use the IP for infinitely. You see here we have the term lease, which refers to the amount of time that a client can use the IP that was given to it. For an automatic allocation, that time is infinite, and it is given by setting the lease time to all bits set to 1. It will be a value of FFFF 4 times 6 times. A dynamic allocation is the normal type of allocation, which gives to a host an IP for a limited period of time. After the time expires, the host can either ask for an extension of lease, or the IP will be taken from that host and be reused for some other client. A manual allocation is similar to a static allocation, with the difference that it is made the configuration is made on a DHCP server, and the administrator does not have to go and log into each computer to statically assign the IP. It is put in this configuration file of the server, and it specifies the host to which we assign the specific IP. Binding, the notion of binding, refers to the collection of the parameters given to a host, which must include at least the IP address. We will see later on what other parameters we can send to a host. The process of DHCP, the allocation of DHCP, is as following. Always the client will start the DHCP process. It will begin in its state, will start the allocation, and it will send a packet called DHCP Discover. This packet has the purpose to see if we have any servers throughout our network. It is sent broadcast because the client does not have an IP, it only has a MAC address, so it will be sent to all the ports that it has. The DHCP Discover packet will be received by a server, which will determine if it has available addresses in its configuration. If it doesn't find any free address, then it will ignore the packet and will not send any reply. If it has a packet, if it has an address available, it will reply with a DHCP offer, in which we'll put the IP offered and the other parameters. The client may receive offers from multiple servers, so it will wait for a time before it chooses an offer, so that it can have better offers than others. So it can choose the best offer from the servers that are configured in the network. After the offer is chosen, a request is sent. This is also sent broadcast through all the subnet for the same reason. At this point, the client does not have IP configured, so it cannot put an IP source in the IP header. So it will send a broadcast message of type DHCP request. When a server receives this request, it will search for the chosen server. If it is the chosen server, it will continue processing the packet. If it isn't, then it will just ignore the packet and will continue listening for other packets. So if we are the chosen server, we check that the address that we offered here is still available. If it's not still available for any reason, then we reply with a not acknowledgement packet, and the client is forced to restart the process. If the address is still available, then we reply with an acknowledgement packet, offering the same IP and the same parameters that we put in the initial offer. The client receives this acknowledgement packet. It checks the address, usually with an ARP request, to see if the IP is not used by some other device. If a reply is received for that ARP request, it means that another device in the network is having the same IP that the server was given to us. So it replies to the server with a decline, which the server will block the address, will release it from the list of available addresses. It will block it, so it cannot be reassigned to another host, and it will issue an error message to the administrator. You can have this type of situation when you both have a DHCP server and you statically configure an IP. So you can offer the IP by a server if you misconfigure it, and you can also statically have this IP assigned to a certain host. Thus, you create this kind of situation, and the client, the DHCP client that detected the problem, will force the server to say to the administrator, you have a conflict with this IP. You have it both configured on a host, but you are allowing me to configure it to someone else. If there is no problem with the address given, then the client will configure its address, and there will be then it will be able to participate in the layer 3 transmission. It can send and receive packets with IP configured. The client, we have the client and the server for DHCP. The client, as I said, sends the broadcast message. Here it's basically explained in written, the scheme up above. In addition to this scheme, we have the extension of lease. When the time that we are allowed to use that IP as a client, we try to extend the lease. We try to get more time to use that IP. We do that by sending a renew message to the server that gave us the address. So we want more time to use that IP. If the server does not reply to us with the extension of lease, we are trying to get an extension from any other server that might be configured in the network. So we send a rebind message, which will be sent broadcast. We send it throughout all ports, just so we make sure that somebody reaches us. Another server may be configured in the subnet, and it may choose not to extend the list of a client if it is not permitted to. Here we have the an output of a client, which it is called the AC client, and the client is based on a state machine. If you want more information, you can look at the end of the presentation. Well, you will see the state machine of the AC client, only if you want more details. And here we can see that it sends a discover packet, then it receives an offer from, this is the server IP. It is the only offer that is received, so it will be chosen by the client. Here you have the DHCP ports. I was talking to you at the at the beginning of the presentation. 67 for client and 68 for server. We send the request with the chosen server. Both the discover and the request are to the broadcast address sent. And we receive an acknowledgement from the server. We are given 26 seconds to use this IP. Bound to means we were receiving the binding for IP 30.1.1.41, and I as client can use it for 26 seconds. In this time I am in bound state. I can use the IP for traffic. After the half of this time is expired, we have T1, which is the rebinding time, which is half of the lease time, and T2, timer 2, which is the renewing time, which is 3/4 of the lease time. And when we reach the half of the lease time, we are trying to extend the lease, and we are entering the renewing state. We are sending a request to the server that originally gave us the address. In this example, the server is down, so it is not responding. We try 4 times to reach the original server. Then we send a request to any server that we might find in the network. This is the rebinding state. After we conclude that there is no other server that can extend our lease, we delete the IP from our configuration. We cannot use it anymore, so we do not generate conflicts by keeping it. And the process of discovery is restarted. We resend a discovery to any possible server that it is in the network. The difference between the request and the discover is that if we have another server in the network and it is up, it may not have the authority to extend our lease. So it may not reply at this point, but it can reply to a discover packet. I think we will stop here and continue with the DHCP server tomorrow, as well as the rest of the information in this presentation. If you have any questions, please address it now, and I will try to answer it to you. Okay, let's see what we have here. I have here a question from Maxime, I think. If you can tell me on what slide are you referring to, because I'm not sure what you see here. Okay, I see here the question if you will own. Oh, okay. So Dorina answered for you. It's referring to the presentation. I think I answered the question about the Wireshark. So any other questions if you have?